Good afternoon, everyone. Today I'm going to be covering in exploit development basics how to bypass ASLR in a 32-bit system, and we're going to have a lot of fun. So I'm just going to jump over to my Linux here and we'll get started. Here's the fun stuff. Okay, so the first things first, I made sure ASLR is turned on. Just cat proc sys kernel randomize VA space, and 2 means it's on, 0 off. If you want to turn it off, you can just use echo 0 into that same file space, but we won't be doing that because we want it on to bypass. Okay, so if we do LDD bin, let's do ping. Over right here, you can see the address right here, and ASLR just changes up the address every time you load it. So then it's harder for us assholes like us to guess it. And as you can see, the address is different. And we'll do it one more time just for good measure. And as you can see, the address is different again. I would like to point out though, there's very few different addresses here. They all start with B75. They all end with 3 zeros. So you can start seeing how we can bypass this just due to the entropy. So what I will do is we will go over to my desktop where my binary files are, and we will open our GDB, which is where I live. And I have this one called vuln. Whoops, let me just start that again. Let me get my PETA plugin. And now the PETA plugin, if you search PEDA GitHub, you'll find it. It's a really simple little Python program that I use in conjunction with GDB. So gdb.q and vuln. Okay, so now we're into the mix. First thing you want to do is within GDB, it prevents, it turns randomization off. So we want it fully on just so we can bypass this properly. So you're going to use set disable randomization to off. That's set. Okay, let's do disassemble the main function. And as you can see here, it's subtracting hex 20 from the ESP when it makes it my stack. I went over stack creation in another video. You can go back and check those out. So I'm just going to print in decibel 0x20, and you start to learn these too as you go along. And as you can see, it's 32 bytes. So then I can do print 32 bytes, and we're going to be looking at about 8 4-byte word areas for our stack. So then I want the return address and I want the 2 functions. So that's going to put it at 33, 34, 35. Let's do display. I'm going to do, let's do 30 words from the stack pointer, ESP. Okay, so now we got that set. Now we look for a string copy right here. This is the function where our input's going to be copied into. So I just hit copy here, and let's put a B star for breakpoint, and let's put in our breakpoint. There. Okay, so I'm going to run this, and I'm just going to put in 4, 5, 6, 7, 8 A's to start, and we'll start dissecting this, and we'll come up with our exploit. So we're at the move before it gets copied into our stack, and here's our beautiful stack. As you can see, this stuff up here, this is all the PETA plugin. Don't worry too much with this up here, just focus on the 30 words in hex right here. And as you can see over right here, here's our stack pointer up here in the corner. I'm going to print, where's our EBP? Our EBP is at 5, 6, 8. So here's 3, 7, 8. So here's our base pointer here, which would mean this here to the right is the return address, and we can do XWX, and this should show libc main when we have a look at it. So, and that's the return address to libc main in our C program. Let's have a look here. Okay, boom. So there we go. Actually, what I should do, I just just thought about it. I should show you the program we're attacking here. So it's a very simple program with an input and a small buffer 8. So we couldn't do the NOP slide like I showed you in the intro to buffer overflows. But what we will do is write our own exploit and take it over anyway. So now that we see where the return address is, this one next to it is the argument count, and you can see it's 2 arguments. And then this here is the arguments themselves. So what I can do, let's do xwx, and let's open up this memory address. And let's have a look at the strings that are on this memory address right here. So I'm going to do x examine string of this memory address. And as you can see, oh, I should have put 2 strings because it's 2 arguments, but that's the first argument there is the file itself. And then you can see our A's as input is the second argument, okay? So now, like we did in dep, what we need to do, we need to fill our, our stack with A's. We need to overwrite our return address, our stack and our EBP with A's right up to here. You can see the 4141 and 4141. That's our 8 A's right there. So we need 4, 8, 12 more. So that's a total of 20 A's. And then we overwrite our system address with, or sorry, our return address with a system. And then we write an exit on the first argument, and then the bin sh as the second argument, and then we'll get shell. Okay, so let's jump into it. So that's good there. So I'm just going to continue, and now I'm going to run it with Python, a little Python. We're going to print capital A times 20. And don't forget to put our little tick in. So now let's see what happens here. Hit next instruction. And as you can see, our stack is now filled up. Now what we want to do, just to develop the exploit itself, I'm going to put B's over 4 B's here on the return address. I'm going to put 4 C's here on the argument count, and then I'm going to put 4 D's on the argument itself. So what we'll do, we'll continue on this process and we'll let it run. And as you can see, because we overwritten the EBP, it's freaking out. So that's a start. That's a good start. So let's go back to our Python. Now we got the 20 A's put in. So I'm going to add 4 B's to overwrite the return address. I'm going to add 4 C's to overwrite the argument count, and I'm going to add 4 D's to finish it off and write over the arguments itself. So let's have a look. Now this is the basis for what we need to do. Next instruction. As you can see, our A's are filled up right up to the EBP. Our B's have filled up the return address, C's over the argument count, and D's over the argument. So this is the basis of what we need to do. Now we need to replace these 4 B's with the system call. Then we need to replace these C's with the exit function, and then we need to replace these 4's here with the bin sh. So, okay, so now we have a good idea of what we're going to do. Let's open another terminal just to keep notes. Here's another terminal. So first we got to find our system function. So we can get that off the libc off our system. So here we go. So here's the address of system, which we can call. Now this way, where we have a small buffer, we can't really put our shellcode onto it. So what we will do, we can call system, and we can call exit, and we can call bin sh all on from the libc library itself. So I'm going to print the exit here, and here's our address for exit. Exit. Let's paste that in there. And then we want our bin sh. And I should say /bin sh because I'll show you the, now this is fine. You have to do with bin sh. So let's do bin sh and I'll show you a little something. So here's our bin sh and this is the proper one. Let me just copy this. Copy. And let's put this bin sh in. So we're starting to build our exploit up. Now, one thing I came across is if you do find and you do bin sh, this is not the same as /bin sh. It comes out with an address. It will not work. So save yourself some time from my mistakes. So there we go. So now we can go back to our Python call again, and we can start filling in these things here with our calls. So the first one to replace the B's, which were right here on the system or on the return. Let's put our system. Now it's backwards. So we need to haul this down here. So let's put this right here. Now, you had to put this in Little Indian convention. It has to go in backwards. That's just the way it's stored. So we put in 10 from right here. Our next numbers during groups of 2 like that. So we'll put 23 and then 5C and then B7. Very good. So now our exit, which we will replace these C's with. 1, 2, 3, 4. Okay, so exit, we can put in 60, 52, 5B, and B7. Everything looks okay so far. Now we got to replace these D's with our bin sh. So let's put in some more X's here. Okay, so let's do 4C and 4D and 6E and finish it off with B7. As you can see, these are all B7, so you can sort of see the entropy there. So now I'm going to run it and just make sure this all goes into the into where it needs to go. So let's hit next instruction. Let's make sure. Okay, so we have our A's filled right up to the EBP. That's good. Okay, so the system should be overwritten with B7, 5C, 2310. Perfect. Let's check out our exit. B7, 5B, 5260. I managed to do this without messing up. Let's see the next one. I bet you I did. And I did too. So 0x086E. So we messed up right there. I knew it. I knew it. I knew it. So let's go back to our run and let's have a look at what we did. Okay, I see the problem right here. So 4C, 4D, we forgot the X right here. See it? So that's the little bit of trouble you can get into with this. But after a while, you get used to debugging it. And it's about a bunch of fun. So let's run this again. And next instruction. So I already know the other ones are good. Let's have a look and make sure our last argument's good. B7, 6E, 4D, 4C. Okay, so we have our exploit already developed. And I'll show you how. Now I'm going to open a new terminal. And what we're going to do now is we're going to brute force the addresses. There's only so much entropy on a 32-bit system. So we can use a while true loop. If I spell it right. Do. And then we'll run our vuln program. And then let me put our exploit in. We forgot the done here, so let me try this again. copy. Let's open another window because that's all messed up. I'm going to CD to my desktop where my file is. I'm just going to put this in just so it doesn't run right away on me. Okay, and then put in a done here at the end. So as you can see, we got while true, do, run the program, and then print 20 A's. And this will keep going until the system function hits this address here, and then we will get shell and take over the system. So this is fun. This is our exploit. Let's run it. Segmentation faults, segmentation faults. Legal instruction, that's good to see. If you just see segmentation faults going straight down, it's a problem. And this may take a couple minutes to get, because we're brute forcing the whole system right now. Legal instruction, floating point exception, core dumped. And we're just trying to brute force. Still going. This may actually take a couple minutes. Okay, that's a new one. Still going. We will get shell eventually. We just need to brute force. I think it could be up to like 65,000 different addresses, but usually you get it really quick. And as soon as that system address hits the same address as it was, then we will jump over and do a full shell. This is one of the longest times I've seen it, actually. And we're still going. The fun of brute forcing takes a while. But usually it's a lot quicker than this. I've never seen it take this long. Of course, when I'm recording it. My old computer's just working away, working away. Boom. Finally, I was just about to quit. I'm like, I'm giving up. But as you can see, sometimes it takes a little longer. My camera was way off. Sometimes it takes a little longer, but we have brute forced ASLR. Who am I? And of course, you can see. Oh, we do have bin SH. So let's hit who. And as you can see, boom, we have shell on the system due to even with ASLR and data execution prevention turned on. So that's bypassing too. My next video, I'm going to add in stack cookies or stack canaries, and we're going to bypass that motherfucker too. I hope you had a good night. I'm sorry you had to watch my segmentation fault go on for so long and just watch me look on it pathetic. I hope you enjoyed. I will be doing another video within the next week on the stack cookies, so look forward to that. Love you guys. Thanks a lot for paying attention, and I'll see you soon.